called because this area is connected with the eye. Just in front of this is a parietal area, connected with many different parts of the body. Still further forward is the central sector, which contains a sensory area for our sense of touch, and a motor area which controls body movement. Overlapping some of these areas and including others is a relatively large region concerned in language and speech. We shall see how these parts of the brain function in human behavior. One method of artificially stimulate different parts of the living brain and observe the results. This can be done in surgery where the brain is exposed. The surgeon touches various parts of the brain with an electrode that carries a weak electric current. No pain at all. And listens to what he says. When the motor area of the central sector is stimulated, parts of the body move involuntarily. When the sensory area of the central sector is stimulated, the patient reports touch, not in the brain, but outside in various parts of the body. A stimulus in the visual area at the back of the brain produces visual sensations such as flashing lights. Still another way to study the function of brain areas is to measure the changes in behavior following injuries in different areas. Let us begin with the visual area at the back of the brain. These areas may be destroyed by disease or by gunshot wound, as in this case, causing partial or total loss of vision. With a metal plate, we can repair the bone gap and restore the patient's appearance, but we can never restore the blindness caused by the wound. The extent of the blindness can be measured in a device called a perimeter. Using only one eye at a time, the patient focuses on a point directly in front of him and reports whether or not he can see a white target move through his field of vision from one end of the perimeter to the other and back again.
No.
As soon as you see it, say yes.
Yes.
You still see it?
Yes. Out. Now. And yes. Yes. Out.
On a chart representing the visual field, a map is made showing where the patient saw the target and where he did not. The black shading indicates areas of blindness. The size, shape, and location of the blind areas depends on the kind of injury to the visual areas. If only the visual area on the left is destroyed, the blindness is in the right half of the visual field, and vice versa. Sometimes these blind areas are irregular islands surrounded by areas of vision. These islands are similar for the two eyes, but never exactly alike. Sometimes the defect is quite small, as in this man, who suffered a glancing injury to the back of his head. In other rather rare instances, only a peephole of vision is left, yet this is enough to enable the person to get along quite well. From measurements like these, we see that injuries to the visual areas at the back of the brain cause regions of blindness corresponding to the parts destroyed. Defects may be more subtle and complex with injuries that are farther forward in the parietal areas. Patients with parietal injuries may have trouble finding their way from one place to another, even in familiar surroundings. The extent of this difficulty can be measured in the laboratory. The patient is given a sort of a map on which a line runs between dots. Carrying this map along with him, he is asked to walk a similar path between the large dots on the floor. While the patient walks, the examiner traces his progress. Still holding the map, the patient continues on his path. So far, no error. Now he gets doubtful, then takes a wrong turn. He is scored for an error. Another way of doing this same kind of test is to give the patient a raised map inside a covered box and ask him to trace it with his fingers while he walks around the floor. Again, the person with the parietal injury does worse than others in this test. Farther forward is a central sector. The back part of this sector, the sensory area, has to do with the sense of touch. If this area, the patient loses some sensation in corresponding parts of the body. We can measure such a loss with a variety of tests. In one test, a series of nylon bristles, each of different thickness, is touched to the palm of the patient's hand, first going from the thinnest to the thickest bristle, then back again to the thinnest. The patient says touch whenever he can feel the bristle, and says nothing when he cannot.
Touch.
Right?
Touch. Good.
The patient with injuries in the central sensory areas of the brain cannot feel the thinner bristles which other people can feel. In another test, we measure the smallest gap between two compass points that the patient can recognize as 2 points rather than 1. When they are close together, he feels only 1 and says 1.
1. 1.
But when they are farther apart, he can feel both points and says 2.
2. 2.
Patients with injuries in the central sensory areas may show a loss of touch sensitivity in all these tests. They also have trouble distinguishing solid forms. Such a patient with injuries in the central sensory areas is asked, without seeing it, to feel a wooden sphere, and then to find the same sphere in a row of many different forms. But he passes beyond the correct sphere without recognizing it at all. Patients with injuries in the central sensory areas may also have difficulty distinguishing between varying grades of roughness, such as these different samples of sandpaper. This patient first touched a roughness of grade 10 in the front row. And to match it with the roughness of one of the other sandpapers in this row, he equated it with grade 15, a large error. We can use the results of such a roughness test on a number of patients to illustrate how an area of the brain can be associated with a specific aspect of behavior. First, the injured brain areas of each of 43 patients who took this roughness test were plotted from their X-rays. 4 of these 43 people had trouble gauging roughness. Here is the plotting of their injured brain areas, 4 in all. The remaining 39 had no trouble gauging roughness. On this chart, we plotted the areas of their brain injuries, 39 in all. Now, let's subtract the injured areas plotted for the 39 who had no trouble gauging roughness from the injured areas plotted for the 4 who did have trouble. The remaining brain area is rather small. Any injury in this area would be most directly related to trouble on the roughness test. With more extensive injury to the central sensory areas, patients may be unable to recognize by touch everyday objects, such as a pair of scissors.
Any idea about what it's made of? What particular kind of material?
Unless it could be rubber. It's the only thing I think of.
It could be rubber.
Yeah.
Well, put it into better hand again and try and see. What might it be?
No, it's
What is it? Take your time.
scissors. Pair of scissors.
Pair of scissors. Okay. Always with that hand you can do it without trouble. With the other one you can't, huh?
That is right.
In the central sector, in front of the sensory areas, are the motor areas of the brain. The left motor area controls movements of the right side of the body. The right motor area controls movements of the left side. Touching an electrode to a certain part of the motor area during surgery makes the patient's hand or thumb move involuntarily. If the same area is destroyed, the hand will be paralyzed. If the injured area is relatively large, the hand may be clenched and resist being opened. Once opened, it closes again. To detect a relatively slight injury to the motor area of the brain, we use special tests like this tapping board, which measures a patient's rhythm and control of finger movement. But when the injury is as large as the metal plate in this X-ray indicates, the paralysis is obvious. Because the injury was on the left, the right side is paralyzed. We are indebted to this patient for his help in allowing us to photograph and study this type of injury. Notice that he walks by swinging his right leg stiffly from the hip. The right arm is bent and half raised, the hand clenched. This patient's injury not only invaded the motor area, causing paralysis, but also involved part of the language areas. These areas are quite large and cover much of the left side of the brain. They are rarely found on the right side. Disturbances in language are complex and often baffling. Patients may not be able to say or to understand words, even though they're able to show us in other ways quite intelligent. This patient is going to listen to a recording of his own head then.
How is the weather out there? Mom, at my house is nearly every night.
All right.
Yep. No. Too fast.
Too fast. All right. I try and do it more slowly. Don't think that I'm sick.
I'm sick.
Right. Fine. You see, I haven't got the time. Okay.
I see. No. You see, I have no time.
Uh-huh. You come back from night problem.
You see.
What's the trouble, Joe? Well, look, let's try it. You come back from night problem.
You see. You. What?
Come back.
Come back from night problem.
Oh, no. Try and do that better. Night problem.
Light problem.
No, it's not a light problem. It's
Light.
N.
L. No, N.
Right. Now say it.
Light. No.
No. Try. Take your time. Take your time.
Wait a minute.
Why do you move your lips before you say it? Does that help?
I don't know.
Are you trying it out for fit or what?
I don't know.
What are
Wait a
you?
minute. N.
You're aware of that you're moving your mouth
Yeah.
without making the sound before
That's
you
right.
make it, isn't it?
Mm-hmm.
Yeah.
N. Night problem.
That's pretty good. Problem. Just say problem.
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 Pretty good. Huh?
To analyze more carefully what this patient's speech difficulty is, we give him a further test in which he is asked to repeat single syllables.
Let's try with some very simple and short ones. Let's say ga.
Ga.
No. Ga.
Wait a minute. E, B, A, B, C, D, E, F, G, G.
Right.
I
Ga.
can't. No, I can't.
You can't say it like that. All right. Then
Ha.
let's say No, not hard.
No, hard.
It's hard. I see. It's hard. Yes. Supposing we say ba.
Ba?
Ba.
Ba.
That's easy, isn't it?
Yeah.
Say da.
Da.
Say ga.
Same thing.
Same thing. Still can't do it, huh?
No.
Well, supposing we say I got it this time.
I got it this time.
Well, why can't you say got if you can't say ga?
I don't know.
You don't know. How come?
I don't know.
From this test, we find that this patient with an injury in the language area can say words and sentences, but stumbles over certain sounds and syllables, especially when he must say one by itself. We have described some specific functions for different parts of the brain, which involve sensation, movement, and speech. But there are more general functions that can be distributed independently of sensation, movement, and speech. Consider, for example, the language areas, which you remember are usually on the left side of the brain. Areas are also involved in mental processes that do not involve speech. Patients with injuries in the language areas cannot easily figure out the following test. In this test, the patient is required to guess the system of a game with these drawings. When the stripes are vertical, he is supposed to point to the circle, and to point to the triangle when the stripes are horizontal. As he guesses each one, the examiner indicates whether he is right or wrong. Patients with injuries in the so-called language areas are slow to discover the system, though it does not involve language. Here is another task in which all patients with brain injury do poorly, but patients with injuries in language areas do even worse. In this task, the patient is supposed to trace the figure at the top of the sheet as it appears hidden in each of the more complex figures below. Difficulty in this task shows up in any patient who has a sizable injury anywhere in the brain. The difficulty does not indicate loss of overall intellectual capacity. It is a subtle but characteristic defect encountered after almost any brain injury. Now let us sum up what we've learned about the function of the brain and behavior. Injury in the visual areas in the back of the brain produces regions of blindness, like the one in this visual field chart. Large parietal injuries can cause trouble with finding one's way about. When the injury is in the sensory areas of the central sector, sensation of touch suffers. With damage to the motor areas of the central sector, there is trouble with movement. And when the injured area is large, a paralysis develops on the side of the body opposite the side of injury. A large area, usually on the left side in right-handed people, is involved in speech. We are still far from knowing the nature of the trouble in every case, and this is a problem for future research. Another task for research is to discover whether there are specific effects of injuries to the frontal areas, those in front of all the areas we have discussed.